Imagine a future where humans venture beyond the moon, not in years or decades but in months or even weeks. A future where the outer planets and distant stars are within our reach. This is the promise of the magnetic fusion plasma drive, a revolutionary engine poised to redefine the boundaries of space travel. The MFPD represents a giant leap forward in propulsion technology, merging the raw power of fusion energy with the precision of ionic propulsion. This combination allows us to achieve unprecedented speeds and fuel efficiency, opening up a universe of possibilities for exploration and discovery. For centuries, humanity has looked to the stars with wonder and ambition. The vast distances between us and these celestial bodies have remained a daunting challenge. Chemical rockets, while powerful, are limited by their fuel capacity and efficiency. The MFPD, however, breaks free from these constraints, harnessing the very forces that power the stars themselves. By fusing light atoms like hydrogen into helium, the MFPD generates immense energy, far surpassing the capabilities of traditional chemical reactions. This energy is then channeled to create a powerful plasma stream, propelling spacecraft to incredible speeds. The MFPD's potential impact on space travel is profound. It promises to drastically reduce travel times, making missions to Mars and beyond a practical reality. Imagine reaching Saturn's moons in a matter of months, or even venturing to nearby star systems within a human lifetime. Such journeys, once relegated to the realm of science fiction, could become the scientific endeavors of tomorrow. The MFPD represents a paradigm shift in our understanding of what's possible in space exploration. This revolutionary engine is not merely a figment of our imagination, it is grounded in sound scientific principles and ongoing research. Scientists and engineers around the world are working tirelessly to overcome the technical challenges associated with fusion power and plasma control. The MFPD stands as a testament to human ingenuity and our relentless pursuit of knowledge. It is a beacon of hope for a future where the cosmos becomes our backyard, ripe for exploration and discovery. At the heart of the MFPD lies the core reactor, a marvel of engineering designed to contain and harness the immense power of nuclear fusion. Within this chamber, temperatures soar to millions of degrees, mimicking the conditions found at the core of stars. It is here that the magic of fusion takes place, transforming matter into energy with unparalleled efficiency. The core reactor is constructed using state-of-the-art materials capable of withstanding the extreme temperatures and pressures generated during the fusion process. These materials, often composed of superconducting alloys and ceramics, possess incredible strength and heat resistance. They are meticulously designed to contain the superheated plasma, preventing it from coming into contact with the reactor walls, which would lead to catastrophic damage. The design and construction of the core reactor are crucial to the overall efficiency and safety of the MFPD. Every component, from the smallest sensor to the massive magnetic coils, is engineered with precision and care. The reactor's ability to withstand the immense forces at play is a testament to the ingenuity of the scientists and engineers who have dedicated their lives to making fusion power a reality. The successful operation of the core reactor is a delicate balancing act, requiring precise control over a myriad of factors. Temperature, pressure, and magnetic field strength must all be maintained within extremely narrow parameters to sustain the fusion reaction and prevent instability. This is where advanced computer systems and artificial intelligence come into play, constantly monitoring and adjusting the reactor's parameters to ensure optimal performance and safety. Containing the superheated plasma generated by fusion is no small feat. At millions of degrees, the plasma would instantly vaporize any known material it touches. This is where the ingenuity of magnetic confinement comes into play. By utilizing powerful magnetic fields, scientists have devised a way to suspend the plasma within the core reactor, preventing it from coming into contact with the reactor walls. The magnetic confinement system is a marvel of physics and engineering. It consists of an intricate array of superconducting magnets, strategically positioned around the reactor core. These magnets generate an invisible force field, a magnetic bottle, that traps the charged particles of the plasma, confining them to the center of the reactor. The shape and strength of the magnetic field are crucial to the stability and efficiency of the fusion reaction. Scientists and engineers dedicate countless hours to simulations and experiments, fine-tuning the magnetic field configuration to achieve optimal plasma confinement. They employ sophisticated computer models and advanced diagnostics to monitor the plasma's behavior within the magnetic bottle, making real-time adjustments to maintain stability. The success of magnetic confinement lies in exploiting the fundamental properties of charged particles. Just as a magnetic compass aligns itself with the Earth's magnetic field, the charged particles in the plasma are forced to follow the helical paths dictated by the confining magnetic fields. This elegant solution allows us to contain and manipulate the immense energy of fusion, paving the way for its practical application in space propulsion. The journey from fuel to thrust in the MFPD is a fascinating process involving multiple stages of transformation. It begins with the careful selection and injection of fuel into the core reactor, where it is subjected to extreme temperatures and pressures, transforming it into a high-energy plasma. This plasma is then meticulously controlled and directed, ultimately ejected out of the engine to generate thrust. The fuel of choice for MFPD is typically a mixture of deuterium and tritium, both heavy isotopes of hydrogen. These isotopes are chosen for their relatively high fusion cross-section, meaning they are more likely to fuse together when heated and compressed. The fuel is injected into the core reactor in precise pulses, carefully timed to coincide with the cyclical nature of the magnetic confinement system. Once inside the reactor, the fuel is heated by a combination of methods, including radio frequency waves and powerful lasers. These energy sources elevate the fuel's temperature to millions of degrees, stripping electrons from the atoms and creating a sea of charged particles known as plasma. This plasma, now a swirling mass of ions and electrons, is susceptible to manipulation by magnetic fields. The superheated plasma, confined by the powerful magnetic fields, is then directed towards the engine's exhaust nozzle. This nozzle, specifically designed to withstand the extreme temperatures of the plasma stream, acts as a particle accelerator, further energizing and focusing the plasma. As the plasma is ejected out of the nozzle at high velocity, it generates thrust, propelling the spacecraft forward.